Hello, everybody. We are Smart Heart.
As a quick overview, our code is broken into 3 sections: data processing, signal analysis, and visualization. We process the raw data using a 2-stage bandpass filter. We analyze the signal to look for wave duration, wave shape, and abnormalities, and we visualize the vectors on a 2D and 3D heart.
So the problem is EKG machines only tell the current heartbeat and nothing else. So what we are trying to do is take an EKG data and make it simple, accessible, digestible, and to give physicians more information and decrease errors.
To do this, we used sample data from the PTB diagnostic database. We imported this using the WFDB record viewer. This was then passed through a pipeline of functions to access it with code. This was then processed through a mix of bandpass and detrending algorithms to give a better signal. An example of this can be seen here. This filtered signal was then put through multiple algorithms to find points of interest, chief of which was the P, R, S, and T portions of the ECG.
So the next 2 portions of code use the methodology by Dr. A.K. Verma, which is the discrete wavelet transform. It's like a Fourier transform, but it preserves time information, which is crucial to our time series data. And the Sim4 wavelet, which is used to perform the transform, emphasizes the R wave because it's similar in shape and symmetric when scaled. So you can see that the lower frequency components, this D3 and D4, are important and extracted for the reconstruction of the detection of said R wave. I will now demo these functions and the missing beats one. So the heartbeat extracts will give you the heart rate by detection of the R waves and find the average distance between them, giving you a start time and an end time for whichever heartbeats you want within your time interval. And for missing beats, you can see within the time interval, it'll output the R wave before your missing beats. And the figure for this shows that we have at 0.845-ish, we have 8 missing beats right after this R wave here. And the very last one is also shown here because there's no data out. The heart wave extraction is important for our next function, which is the gradient angular field. It's a time series to image conversion, and it utilizes polar coordinates and the gradient angular field matrix to give an image depiction of our data. And for a healthy patient, there is a consistent coloration around this cross here, whereas in the unhealthy patient, we've got difference in coloration. And further work would be to explore the significance of the difference in these images.
For the 2D and 3D hearts plotting, what we did is we took a graph and then we overlaid a picture underneath for the 2D heart and a 3D heart over for the 3D heart.
We used data from one of the patients to get the information for the signals that we plotted on the 2D and 3D versions of the heart. We plotted based off of the wave detections that we found earlier, and we're able to put them on the 2D heart, which you see on the right-hand side, and the 3D heart, which you see on the left-hand side.
In terms of final results, meaning what the physician will see, we'll see a filtered ECG graph, 1 heartbeat of interest, the location of an R wave before a missing heartbeat, and a 2D and 3D graph with lead vectors. And a special thanks to Dr. Fong for giving us a 3D model of the heart, and Dr. Gundas for providing the groundwork for the math behind the heart vectors and the idea for the project.